Well, I have 9 o'clock, so I'm going to open up and start the meeting today. Welcome to everybody. Welcome to today's Arctic Research Seminar, which is hosted by the Arctic Research Consortium of the United States, or ARCUS. My name is Betsy Turner-Bogren. I'm a project manager here, and I'm joined on the ARCUS team by Stacey Stout and Kuba Jenda. Today's seminar will feature Dr. Gerald Frost, our senior research scientist with ABR, or Alaska Biological Research Incorporated in Fairbanks, Alaska. We have a couple of housekeeping items before our presentation begins. I'm trying to advance my screen and not having success. Oops, there we go. You have two viewing options available today, gallery view and speaker view. Gallery view allows you to see the webcam of other participants online, and speaker view allows you to only view the presenter's webcam and presentation. To switch between those views, please use the button at the upper right-hand corner, which is indicated by the red arrow. Your Zoom controls, including the chat function, can be found by hovering your mouse over the bottom of your Zoom window. I seem to have a glitch, and there we go. You are invited to chat with other webinar participants at any time. To do that, click the chat icon at the bottom of the screen and select the name of the participant with whom you wish to chat. There's also an option to chat with everyone participating in the webinar. Questions will be addressed at the end of the presentation. If you're joining by Zoom, please type your questions into the chat window at any time. I will read the questions aloud at the end of the presentation during the Q&A. If you are joining today by the YouTube live stream, please type your questions into the live chat window, and Kuba, our facilitator, will share your questions with me and read them, so I will read them aloud. Please note that there's a 10 to 15 second delay between Zoom and YouTube live stream. And if you're joining by phone, you will need to raise your hand by pressing *9 on your phone. Unmute yourself by pressing *6 to ask your question aloud. For any technical questions, please contact Stacey Stout at email, and her email is Stacey, S-T-A-C-E-Y, at arcus.org. I am having trouble advancing my screen to the next. There we go. Thank you. Before we begin, we'd like to thank the National Science Foundation Office of Polar Programs for their financial support to ARCUS and to this seminar series. And I don't understand why I'm having trouble advancing my screen, but I certainly am. Now I'd like to welcome today's presenter, Dr. Gerald Frost. He is an ecologist with a multidisciplinary research background focused on Arctic tundra and boreal forest ecosystems. He earned a bachelor's degree in biological sciences at the University of Alaska Fairbanks in 1999 and a PhD in environmental sciences at the University of Virginia in 2013. JJ has accumulated over 20 years of field experience in Alaska and northwestern Siberia. His recent work has focused on tundra vegetation dynamics, interactions and feedbacks between vegetation and permafrost, landscape change detection, and long-term monitoring of vegetation permafrost. JJ's research integrates field measurements with a variety of modern and historical remote sensing data sets to elucidate current ecosystem conditions and long-term change. JJ lives in Fairbanks, Alaska, where he is a senior scientist with ABR, Alaska Biological Research Incorporated. Today, JJ will be discussing the greening of the Arctic, causes and consequences of change in the Arctic tundra biome, seen through the lens of satellites, field research, and local observations. At this point, JJ, please take the screen for me, and everyone else help me welcoming Dr. J. Frost. Thank you.
Okay. All right, everybody. Hopefully everybody can see my title slide and can see me presenting on my back porch, which I've never done here in the heart of the boreal forest. It's right here. And so I think one thing I'd like to do with this talk is I know in our current times with COVID and the pandemic, you know, a lot of us are just feeling stuck. You know, nobody's able to travel. So today, at least for the next hour, I'd like to take you on a little journey, and we're going to go north and take a look at one of my favorite topics, the Arctic tundra part of the Earth, and take a look at it through multiple lenses, as the title slide indicates. So first, just a quick roadmap to how we'll go about things. Start out with some really like a big picture look at the Arctic tundra and how it fits in terms of a global context, how it fits into the rest of the world. And we'll take a look. There'll be a lot of photographs from the field and also from the air or from space, of course, and looking at the tundra in its various forms in different ways. So we'll start out primarily from space, and then as the talk proceeds, we're going to drill in closer and closer and closer until hopefully you have some sense of what it's like to be standing there on the ground looking at tundra and all the landscape features that go along with it. And then at the end, I'd like to try to summarize some of the things that I've learned speaking with Arctic people about their observations and their perspectives, which in many cases extend back much farther than our satellite record does, or in the history of Western science in the Arctic. So from a global perspective, we talk about Arctic tundra, and when I talk about Arctic, to me, that really does refer to that sort of treeless fringe of land that's encircling the Arctic Ocean, that northernmost biome on the planet. And so biomes, briefly, it's a global classification system that describes different broad types of climate and the vegetation that tends to accompany that climate. And of course, most of the world's population lives in temperate latitudes and biomes in the tropics and in the temperate zone. Not so many people here in the boreal, and fewer still in the Arctic tundra. But that whole concept of biomes began back in the early 19th century with this fellow, Alexander von Humboldt, one of my heroes. But he noticed, traveling in the Andes Mountains in South America, these recurring patterns where as you moved up the mountain chain, the climate changes locally, and there's very predictable changes to the vegetation as you move up and down. So within a very short spatial distance, just from the base of a mountain to the summit, he started to note these patterns and how there's a zonation of vegetation on the mountain or on the volcano. And it didn't take long to realize that you can actually, the same concept applies globally. And for example, in the Andes, if you move from the summit areas, you're seeing something that actually looks rather like tundra. Towards the summit, few trees, and as you move down, vegetation changes quite predictably until you get to low elevation areas and you've got big canopy trees and forests. So he wound up applying the patterns that he noted and applied that to think about global scales. And this is a pretty interesting map. We're going to now depart the tropics and the temperate zones and focus our attention to the north. And I'm not sure, hopefully you can see my cursor, but this is a pretty interesting map. You'll notice there's a lot of unknown territory up there in the far north, and that's where we'll concern ourselves now. So let's go there. So first, the boreal forest zone, where I'm currently located, you can see in the background. This is a really big biome. There's a lot of Earth's surface that is covered with boreal forest, and part of that is because most of the continental land masses on Earth are kind of packed in the northern part, in the northern hemisphere, and so it's a very extensive area. We all know Alaska is a big place, but when you put it in this context, I mean, you understand just how big the boreal forest or the taiga zone is. And we're going to head north to the northern margin of that biome and enter the tundra. And this is just a passage from Russian literature to me that's pretty inspiring. And let's join those birds of passage and find out just where that boreal forest margin is and what we find beyond. And that is shown on the right in that multicolored map. And that's just a depiction of the Arctic tundra biome as we understand it. So it's excluding alpine areas like the Rocky Mountains, different places, although are certainly tundra environments as well. But these are places primarily that are quite close to the shores of the Arctic Ocean. And we understand that Arctic Ocean is very often covered in sea ice. So that has a very strong influence on the conditions on land, and is responsible for that large part, that colder climate in the Arctic. But the Arctic tundra is not just one monolithic, homogeneous zone where everything kind of looks the same. There's actually a lot of zonation within it. And if you think right along the southern margin of the tundra, where you start encountering trees, no matter where you are on the planet, that place tends to coincide with about that place where the summers are reasonably warm, and you've got a mean annual July temperature of about 10 degrees Celsius, 50 degrees Fahrenheit. So that's at the southern margin. If you go into the coldest parts of the Arctic, so way up there where there's a lot of sea ice, you see there's a very strong climate gradient within the biome. So some of these northernmost locations in the high Arctic, you've only got very brief summer that's actually quite, just barely above freezing. So how these different parts of the Arctic are going to respond to climate change, increases in temperature and other conditions, could really vary depending where you are along that gradient. So just some visuals now. We're going to pretend we're moving north right at the edge of the boreal forest, and we'll just take a look at some different types of tundra. So this is an example of a very abrupt shift from forest to non-forest, and you see that along an elevation gradient just on a mountainside. So it's very abrupt in this case. But usually in the boreal zone, as you move north, you see not a distinct abrupt tree line, but something that's very diffuse. And this is an example here in Alaska where you see a lot of trees, but a lot of open areas that are starting to look quite a bit like tundra. As you move further north, those patches of trees are getting smaller. They're just restricted to certain areas until finally the last patches of forest start to winnow out, and eventually you're really in the Arctic tundra zone, and you might see some larger shrubs and maybe some scattered trees along rivers and so on. But obviously some big changes in the structure of the vegetation. And then across the Arctic, this is an example of a transect that I had the good fortune to be involved with, doing field work at various locations in northwestern Siberia. And just gives you some idea of the changes in vegetation as you get further north into colder environments. The vegetation really does change quite dramatically until in the far north you get sort of this partially vegetated tundra that is dominated by lichens and mosses and things like that. But across the Arctic, we understand that the Arctic in general is very much in a time of rapid change. And maybe the most widely known aspect of that has to do with the marine environment, so sea ice, which has been declining rather precipitously in recent decades. And at least for me as a terrestrial, Earth landlubber, so to speak, that's pretty easy to understand. You've got an icy surface versus a surface of open water. It's kind of binary. But the same things that are driving sea ice decline are certainly creating changes on land that are quite important, and of course will be the topic of the talk today. And this is just a visualization on the upper left that gives some idea that climate change and warming is most pronounced at high latitudes. So this is something we call the Arctic amplification. So it's where we see the most dramatic changes. And that has implications, of course, within the Arctic for vegetation, for frozen ground, soils, permafrost, and then also in terms of how energy and elements and how carbon is exchanged between the living ecosystem and the atmosphere. So those are very important topics that really make the Arctic really relevant to what's happening at a global scale. And we understand that as time passes in a warming climate, we would expect the boreal forest to sort of creep its way northward. But trees like these behind me, they don't do anything particularly fast. This is not a really rapid process. But there are a lot of rapid changes happening within the tundra. And as I've heard it said, the map is changing. So we'll look at a lot of maps in this talk, but these aren't static things. These do change over time. And we'll get into some of the types of characteristics that are changing in the Arctic. So we're primarily concerned with vegetation when we talk about the greening of the Arctic, but it's important to understand that The vegetation is, is obviously is very closely linked to the physical environment, and the sorts of information we get from satellite imagery and other sources of data are being influenced by changes in, for example, not just in the vegetation, but in surface water. There's a lot of water, lakes, rivers, ponds, big and small, across the Arctic. So dynamics there, that's going to affect that signal that satellites are receiving from space. And then likewise, there's features that are not even at the surface, but are just underneath, which are really pivotal in controlling vegetation and its changes over time. And permafrost, here, this is a pretty spectacular exposure of permafrost, a very ice-rich permafrost that I visited in Russia some time ago. And again, related to permafrost, permafrost is really interesting thing. It creates these very interesting superficial patterns on the landscape. Like in this case, we're looking down from a helicopter at vegetation growing among frost boils and other pattern ground features that are formed by freeze-thaw processes in the ground. Soils, obviously, again, a lot of this is subsurface. So we have to, it becomes critical so that we integrate field research and boots on the ground with the satellite record to really understand change in the Arctic. The sea ice system is really important for Arctic tundra, again, because of its impacts on the local climate. A seasonally ice-covered ocean has a really big impact on temperatures on land, and as that sea ice becomes less frequent, we expect conditions on land to change as well. Animals and also insects, these can have a big impact on the health and the productivity of vegetation in a given location in a given year. So, animals really are important, not just the big ones, but the little ones, insects, and also pathogens, so pests that might affect vegetation. And then another thing to keep in mind is there's a lot of rapid change that occurs with disturbance. In this case, we're looking at an air photo of a fire burning in tundra down in southwestern Alaska. So clearly, these kinds of processes can have a huge impact locally on the vegetation conditions, and all of these things are captured to some extent in that satellite record that we'll dive into. So before we head to space, we'll just maybe take a step back in time. And this is an interesting photo in southwestern Alaska around 1918, an area near tree line. And I actually went to that same spot, took a photo some years ago, and that's the scene today. So obviously, very dramatic change at this site here with the spread of these small birches and some spruce trees in a pretty short period of time. Similarly, this is elsewhere on the highway system in Alaska, kind of a mountainous area. You can see this sort of patchy woodland with some spruce trees scattered in the distance. And if we look at today, you see the number of trees, their density has really changed quite dramatically. So these are sort of anecdotal observations, just a particular location and how that space has changed under its own set of circumstances. So it begs the question, is that representative of a broad scale pattern? And that's really what's motivated our use of satellite technology to really try to take that step back and look at the entire biome and the entire globe. So let's head into space, or at least look through the lens of satellite systems that have been operating. So the Arctic is a really remote area, as I think most of y'all know. It's hard to get anywhere. It's expensive. It's challenging to do field work. And remote sensing, and by that we're basically sensing the environment without actually being there, actually physically touching it. With satellites, that helps us overcome a lot of that remoteness, right? But it's still difficult because the Arctic is, since we're interested in vegetation, we're interested in sensing the environment in summer when the snow's gone and the plants are active, and that's a short period of time. And during that period, many days are cloudy, so you can't get good information when the landscape's cloud covered. And like I said before, permafrost is a critical component to understand, but it's down there in the subsurface. It's hard to get at it from space. But it's an exciting time to be doing this kind of work because of all of the tools in the toolkit, basically, and then the different technologies that have come online and some technologies that we've had actually for a long time and can build a data set looking at change over time. So a quick rundown, when we get into talking about satellite systems and remote sensing, it's very easy to get bogged down in jargon and some really long acronyms. And I'll try to minimize that, but all I'm showing here are a series of some of the more important satellite systems that Earth scientists like myself are using. AVHRR is one of the oldest. It's a coarse resolution system and 7-kilometer pixel size. So it takes a snapshot of the entire globe every day, but it's emphasizing certain features, just like a camera that you might have. If you have a big wide angle camera, gives you a very broad view. And then you might also have a different lens for your camera that you get a progressively better zoom lenses, for example, to get a closer look. So each of these tools is going to emphasize different features, just like the camera that's trained on my face here. A different sort of view, you know, looking at the view you have of me now, you have no idea that I'm actually a pretty tall guy. So you need a different view to understand that. So these different tools give us different ways of kind of peeling back and getting into some of the dynamics in Arctic tundra at different spatial scales, from global to local, or the scale even of an individual plant. In terms of a timeline, you know, really this sort of monitoring began around 1982 with that AVHRR satellite, and that is really the backbone of our long-term satellite record for not just tundra, but global vegetation productivity. It has its own strengths and weaknesses, as do these other satellites, and we'll focus mainly on AVHRR, but we'll look at a few of the others as well. So how do we monitor greenness? I think we understand, obviously plants are green, but how are satellites actually getting at that, and how do we do quantitative measurements of that? So a quick little bit of physics. We won't stay here too long, and of course some of y'all might recognize the graphic here from a wonderful classic rock album. But we understand visible light. I mean, that's obviously what we see, and what's shown in this little graphic. We understand sunlight is refracted, and we understand the different colors within the spectrum, and that's just a really narrow window of the spectrum that our eyes are sensitive to. But on either side of that, there's other wavelengths that we can't see, but we can develop satellite sensors that do sense those, and they actually prove to be very useful for studying vegetation. And I'll talk mainly about metrics that have used the Normalized Difference Vegetation Index, or NDVI, and that's quite a mouthful. I'll try to just refer to that as greenness, a measure of greenness. It's an index of the amount of photosynthetically active green vegetation. And the basis for it is that green vegetation has very, really unique properties compared to other non-vegetated surfaces in the way that it absorbs certain types of light, but reflects a different type. And in this case, NDVI takes advantage of the fact that green plants are very effective at absorbing red, or visible light, but are also very effective at reflecting near infrared light, so light that's just outside the visible spectrum. They don't use it for photosynthesis. They don't use it for anything. They just try to get rid of it essentially and reflect it. And that's very different from how a pavement, or your rooftop, or a sandy beach, or just any non-vegetated surface doesn't behave that way. So we can use that as an index. And I'm going to real quick segue to an animation that'll hopefully give you a little context for how we can learn from using that index. So bear with me. And a real quick animation. And this is an animation that's showing global NDVI through different months. So we're just looking at an animation as it's cycling through different months of the year sequentially. And if you just train your eye in the northern hemisphere, you'll see as we come out of winter, there's this sudden green flush that extends all the way up to the high latitudes. And that's showing spring green up. I mean, that's what's happening here in the boreal forest over the last month. It's happening on the tundra right now. And of course, then you see the waning and the senescence of vegetation in the fall. So this is, and if you look elsewhere on the globe, there's some very interesting patterns that tend to be more related to rainy season, wet season, for example, in the tropics. So this is this use of NDVI is a really effective tool. In this case, we're just looking at seasonal change through different years. So now we're going to go back to the presentation. Okay. Right. So now we're gonna use the NDVI in a different way, and what we want to see is not seasonal changes, but what we'd like to do in this case is take a snapshot of the Arctic at the peak of the growing season. So in the middle of summer, when everything's greened up, you know, this is usually sometime in late July, early August, when you're at high summer. And if you can take that snapshot and then compare that snapshot that you take each season, you string them together, and you can get a plot like this in this case. And this would be, if we see a trend, in this example, an increasing trend, that's what we mean by greening. And so that's a metric of vegetation. And as the talk goes along, we'll look at some examples of what would look different to you on the ground if you were able to stand and reoccupy the same location throughout that time series. And that's one of the big things that people like me are really interested in learning more about, to understand, you know, what are the changes and what do they mean? What do they mean for people? What do they mean for the rest of the planet? So this is a figure made by a colleague of mine, Uma Bhatt, that is showing the greenness trends across the circumpolar tundra biome. So the colored areas are tundra, essentially. And the colors are fairly intuitive. And there's some interesting patterns here. This is looking at from 1982 through last summer. And in general, you see greening across most of the Arctic, but there's some real hot spots, northern Alaska being perhaps the most prominent one. Very strong greening there. And in general, strong greening in the southern part of the biome, so along the southern margin primarily, but with some variation too. You see some areas in the Canadian high Arctic that appear to actually be declining in greenness, browning, and then also in southwestern Alaska. So it's not a uniform picture everywhere, but if you do distill the Arctic into one unit and just take an average, we're certainly seeing a strong trend in increasing greenness. So that's looking at it in a map. If we instead just summarize, and just to give you a little context of what greening and browning, some different forms of that, you know, you can have some examples like we saw in the repeat ground photos, increasing shrubs and trees. That's be a very strong driver of greening. But you can have a lot of things occur that would cause plants to be stressed, and maybe they're not growing as well, or they die, and that could certainly cause browning. And so there's a lot of different ways that either of those things can happen. If we look at the satellite record in this form in a plot, what we're looking at here is just a average NDVI value or greenness value for each year for the entire Arctic, just the entire Arctic distilled to a single point on the graph for a year. And there's three lines. The center one is really the one to really pay attention to. That's summarizing the entire Arctic. And then the lines above and below, the top one is just the Eurasian part of the Arctic, and the lower line is just the North American part. So we're seeing, you know, a lot of peaks and valleys, certainly variability. But overall, over the length of the record, there's a lot of ups and downs, but in general, it is an increasing trend. And there's a few features in the graph that are pretty interesting. One year that always sticks out is 1992, and that is 1 year following the Mount Pinatubo eruption in the Philippines, which put a lot of ash up in the stratosphere, and it actually caused some cooling in the Arctic the following summer. So that's one of the lowest years in the record. We see some other ones, particularly later in the record, just in the last few years, and I'll talk about those a bit as we go along. A similar map that we looked at before, this is just a different way of summarizing greenness. Rather than taking that peak value from midsummer, we take a selection of values throughout the growing season. So throughout the 3-month growing season approximately. That gives us more of a picture of what's happening throughout the season. And it's emphasizing perhaps different aspects of change and how the plants that are growing out there, how they're responding to conditions. So the general pattern is roughly the same. Northern Alaska again sticks out as a hot spot of greening, Canadian Arctic the opposite, and Southwestern Alaska also the opposite. So a little more complicated here, and likewise in the plot, a bit more complicated too, a lot more variability. Again, we see 1992 is really low in the record, but also 2018 was really low, especially in North American Arctic, where perhaps in the high Arctic of Canada and Greenland, they had a really late spring and a lot of snow the preceding winter. So a lot of what ordinarily would be part of the growing season in that year was essentially snow covered. So it really created a really strong dip in vegetation productivity, and it'll be interesting to see what happens in the coming years. So I think looking at that global perspective is really interesting. There's a lot of patterns to drill into, but it still is maybe a little abstract understanding, what do these trends really mean and how do they relate to change on the ground. And so we're going to shift now from AVHRR to a much different sensor. This is Landsat at about 30 meters resolution, so much finer scale. It's sort of like the telephoto lens, so to speak. And we're looking at, this is an old photograph from the late 60s of just a meandering river in Arctic Russia in this case. And this is nice. These are good places to look to try to get a check on are these NDVI trends making sense in terms of other changes we understand are happening on the ground. So like most rivers do, they move around, and so these outer bends tend to erode, cut bank erosion, and the inner bends tend to deposit new material that gets colonized by vegetation. And if we advance the slide, you'll see that the river channel has moved. So there's areas that have lost vegetation where the river's basically taken out the cut bank, and then places where new vegetation has become established. And if we superimpose a map of NDVI trends, we see the patterns that we should see. Strong greening in these inner bends where you've got a lot of willows and riparian vegetation establishing. Browning on these cut banks on the outside where you've replaced essentially tundra with water. So that's a really good check, and it sort of tells you that the information the satellites are collecting is, that it's really relevant to changes that we know are occurring. So with that, we can begin to piece together different satellite records and compare them. AVHRR is telling us a pretty compelling story of greening over time, certainly with some ups and downs, but we can start to use more recent sensors to provide a little more context and understand what's happening at finer scales. So if we look at this place in southwestern Alaska that appeared to be browning a bit in the AVHRR record, this is the Yukon-Kuskokwim Delta, an area I've been active in for the last few years. And I'm quickly going to just put on several maps. These are trend maps that are just focused on the YK. And the AVHRR record here is kind of mixed. You see some areas of greening, some browning. But MODIS, which is a much more recent advanced sensor, started in 2000, and Landsat about the same time. Those two sensors actually tell us something rather different. They're actually indicating that it's primarily greening there. So this is pretty interesting. I don't want to get too bogged down in trying to compare different satellite records, but I think it's worth noting is, it could be the case that this greening that we've been seeing from AVHRR over time is possibly maybe even more widespread. That's certainly what MODIS and Landsat are telling us in this particular part of the Arctic. But those other satellite systems are becoming more and more important as the years pass and the period of record grows. But we still need to drill in, and we're gonna start heading back to Earth and on into the field. But first, just a note that there's a whole another class of satellites out there, which I think we've become more familiar with in our daily lives, that provide really high resolution imagery. This is the types of imagery you see, for example, on Google Earth, and you can zoom in at your own house, and you can see your car in your driveway, or you can look at all figure out how to get somewhere. And this high resolution satellite observation has really kind of revolutionized a lot of the way we do Arctic science. But it's actually not as new as most of us think. We think of this as starting maybe around 2000, 1999 with the first commercial satellites, but in fact, we were doing high resolution observations from space starting back in the 60s. And the reason we were doing that was certainly not to look at ecological change in the Arctic. It was to monitor what's happening in the Soviet Union. And the Soviets were doing the same thing to us, right? So these technologies evolved extremely rapidly. And they use it's kind of diabolical to think that they even functioned at all. They functioned using physical Kodak film. There's a very elaborate system in order to get this stuff up into space and get the film back. It's pretty interesting. But here's an example of some of that imagery, and we're looking at what's today is Reagan National Airport in DC. And I just want to call your attention in this photo, just try to wrap your head around, it's the mid 60s, and we're looking at DC Airport from space. And if we look at the aircraft that are down there, the backbone of the commercial aviation system in the US, they're piston engine aircraft. There's no swept wings, there's no jets. So we're kind of somehow in this space where we're entering the space age, but not fully into the jet age even. So it's a really interesting and pretty unique resource for looking at environmental change. And it's actually all publicly available now. And it's very useful because so much of the Soviet Union occupies boreal forest and Arctic tundra environments. There's a lot of imagery that is very high resolution that lets us step back into the past. And in this case, an area with, you can resolve individual alder shrubs in this case. And we can look at the same area with modern imagery, and we can record change in a pretty detailed way. So this is an example of shrub expansion in the low Arctic, and that we believe is one of the primary mechanisms that is driving Arctic greening, is an expansion of these shrubs, where you're going from a sort of a two-dimensional surface of moss and very low-growing vegetation to something that's growing up and forming a canopy. So that would be a very strong driver of greening. And we're seeing this in a lot of the Arctic, particularly in the warmer parts of the low Arctic. Another example, slightly different 60s era sensor. The dark patches are basically shrub thickets. It's a place in northwestern Siberia. A modern image, actually that image itself is now almost 20 years old, so it'd be pretty interesting to follow up and see. But in general, some of the red markers are calling your attention to areas where the shrub abundance is increased. So again, this we would expect would be a very powerful driver of greening. Okay, so let's now head into the field. And doing field work in the Arctic, in the introduction Betsy gave, I've had the good fortune to go to a lot of different places. And I just want to have a little fun here and just let everybody get an idea of what it's like to get to these places and to work in the field. So different modes of transportation, inclement weather that's going to cave your tent in, stressful times, where things aren't going quite as planned. One motto you've really got to keep if you're a field worker in the Arctic is, you must relax. You must relax under any circumstance. Different modes of transportation. This is not an uncommon thing to see in northern Siberia. Reindeer, very important for getting around. You can travel by ship, icebreaker, let's go on a cruise. Motto number 2, have a good trip. So no matter what happens, have a good trip. In this case, hitting some heavy weather. This was heading into the high Arctic some years ago in Russia. Helicopters, aviation in general, obviously critical for getting around. Again, a Russian example here. Different accommodations. So this would be your Arctic Airbnb. It doesn't look all that inviting, but you make do with what is available. Plush comms. So doing field work in the Arctic is a memorable experience. A lot of cherished memories I have, and thanks for indulging me. I just wanted to share some of the some snapshots of what it's like. And the people you meet, and in this case, the dogs, you build bonds with the people around you doing this kind of work that can last an entire career or a lifetime, and friendships and so on. So there's a lot that goes into doing this kind of work. And it's hard to do well, but it's really critical for putting that satellite record into context. So for the last part of the talk, I want to drill into an area, mentioned the Yukon-Kuskokwim Delta of southwestern Alaska, a really large region, one of the most biologically productive parts of the Arctic, and one of the most inhabited by people. So there's a lot of people living out there in villages, practicing subsistence lifestyles. And so the sorts of changes that are happening in the Arctic and in this region, they really do matter to not just to the rest of us around the globe and how it affects our climate, but for local people. And so the Yukon-Kuskokwim Delta is somewhat peculiar in it's some of the southernmost tundra that exists on the planet. So it's pretty warm and it's also very low lying, as is much of the Arctic tundra biome. It's close to the ocean. So much of the YK is right down near sea level, and there's permafrost there, but it's very close to that point where it's thawing. And so it's an area that we think is very susceptible to rapid change associated with sea level rise, permafrost thaw, and these sorts of things. But you layer on that people are there, there's villages, there's infrastructure. These things are expensive to build and critical to the people who are living there. So it is an area that's very dynamic, very vibrant place, but also it's got a lot of challenges that's related to environmental change. And to give an example, these are just some scenes from, give you some idea of the variability in the landscape, different parts of the region, what they look like on the ground. So you've got areas like the Yukon River Delta, you get these big shrubs, very productive ecosystem, lots of moose. You go elsewhere, and the tundra is not everywhere the same, and it's responding in different ways to climate change, and that is ultimately all contributing to this greening signal that we're getting. I've mentioned tall shrub expansion. That's certainly important on the Yukon Delta. Disturbances like fires are active out there, and permafrost degradation. And this is, the same really could be said for many parts of the Arctic. So how do we get from pixels in a time series to understanding what's happening with vegetation? So at the plot level, so at a scale that makes sense to you and me just walking around, we can make detailed measurements of vegetation, and in some cases, we can do this over time. This is work that a good colleague of mine, Tor Jorgensen, has done for many years at a site and has a whole network of plots sampled in different time periods, and we can track the fate of each of these plots through time and look at the same place. And you can see here just in photographs vertically. You can look at these photographs alone and just see certain types of change. This one perhaps the most, where you had a flood event and actually erosion along a river where it's basically taken out the plot. So in each of these cases, you can make some predictions. And in this particular one, of course, we'd expect that actually there must be browning is occurring there. There's less green vegetation. Perhaps some of the other plots, it may not be so obvious what the changes might be. So it isn't just the plants that are affecting that greenness index. I mean, it's the primary thing, but as we've mentioned, surface water and permafrost are very important. And permafrost in particular just throws a real curveball on just about anything. When you look at change over time, it's such a dynamic phenomenon and can be difficult to study. But in the Yukon-Kuskokwim Delta, basically you get these situations where you develop permafrost and ground ice, and that essentially jacks the surface upward, and that can be very obvious in the field. And you'll notice the vegetation on either side of this sort of dividing line changes, and many other aspects of the growing conditions change as you're on a permafrost environment to a non-permafrost environment. And some of the studies we've been doing there are actually using the vegetation as a method of understanding what's happening with permafrost, and doing some things to sense permafrost directly, like using a thaw probe, for example, to probe down and determine where there's frozen ground. But on the YK Delta, often the topography, the little topography that you do see is related to the presence of permafrost. And so a common approach is we get out in the field, we collect a lot of measurements right there, and then use some form of remote sensing data and make a map and bring those two data sources together, and then assess how we've done, and if possible, we make improvements. And in this case, this is just a visualization where we've mapped the distribution of permafrost in this area. And we've been doing some work in this area in cohort with some people from a local village, Chivac. And this is an area where permafrost really is disappearing. And I bring it up in this talk because that's very relevant for understanding greening trends. It's actually a way that you can drive browning. If you have a permafrost surface and that surface thaws and the surface collapses, in many cases it'll turn into a small pond, and you lose the vegetation. So that's actually one way that you can have, browning occurring. But in this example, it's useful to think, like, how does this matter for people? And in that part of the YK, it matters actually quite a lot, because these permafrost areas, they're kind of high and dry ground. They're used for all manner of things, a lot of subsistence activities. They're good places to camp, different seasonal activities, a lot of cultural sites associated with them. It's important for animals. This is just one example of a migratory bird that's fairly unique to that part of Western Alaska. And they're really reliant on these permafrost features, in particular berries that grow on the shrubs that are associated with these environments. So this is an example where, there's more going on. In this case, what does browning mean for people and for resources that we care about? So one way to get at that, obviously, is to talk to people and understand, what have they seen and what are their concerns? What do they think? Where do they think things are headed, and what do they think has caused the changes that they've seen? So this is a gathering I was involved with on the YK, and talking to these folks, particularly in the front row. These are folks whose their own lifespans and their memories, they extend back before that satellite record, even that 1960s satellite record. So trying to get their knowledge while they're around is I think a really important thing that maybe isn't getting as much attention as it should, though many people are working on that, to try to capture that while that generation is still with us. And I just offer one little quote here that I thought was particularly, it was pretty moving, actually, and just understanding how folks are adapting to change. And change in some sense is nothing new, but it's the combination of different changes occurring together and the speed that those things are happening today that I think are creating some challenges. And so you see that quote there. We're getting towards the very end here, but I just, there's a lot of ways to perform science in a way that is that involves local people, and I think there can be a lot of really useful cross-fertilization there, and it's also helpful for the younger generations coming up in these villages, to the extent we in the science community are able to engage them and give them tools to explore their own environment and understand change. And this is an example, again, using this the satellite record. Within that little comparison, this is around a village in Western Alaska. There's been a lot of different forms of change, whether it's related to shrubs or coastal erosion. Again, all things that are very relevant to greening at local scales, and putting this in a form that people can use in the villages. And hopefully in the community, it's very important for us to understand these global scale patterns and link it to the global system. But I think it's very important too for people like me to be able to address questions that are of interest and really of concern to Arctic people. So in this case, permafrost is really a lot of very negative impacts. But then there's some others that, that may be a little mixed. For example, shrub increase in this area seems to be being accompanied by a real expansion of the moose population. So moose are a really important subsistence resource in this area today. And that really that's kind of a byproduct of this greening that we've observed out there. But, when you fill up what was an open landscape with lots of shrubs, and nobody likes to bash through alder thickets, it's something that people really do notice. So it looks like I've left time for questions, but oops. some quick conclusions. It might have some sort of timing. Okay, it's going to stay there. So Arctic greening, it is an evolving story. We did see that year just recently of cold summer in North America. So it's not a monotonic increase every single year. There's lots of variability, but I think as the period of record grows, we do see the big picture, which is that the Arctic biome, that there is a lot of change, and most of it does seem to basically translate into an increase in the amount of vegetation in the Arctic and its productivity. But stay tuned. And some of the changes we looked at, particularly on the YK, I think it kind of challenges our concept of what is Arctic. And if we project forward 50 years and you've got areas today that have seasonal sea ice or spring sea ice, well, in 50 years, they may not. And the permafrost may be absent. And do we consider that still Arctic? You know, it's maybe just a point to think about. But in terms, it has real implications for infrastructure and the lifestyles of Arctic people, big challenges that are all kind of wrapped up underneath that picture of greening and browning that we've looked at. The next, integrity and continuity of data sets. So I kind of threw this in here, not so much about the satellite record, but when we consider COVID and this unique circumstance in this year, there's a lot of, like, I'm not doing much field work this year. Many people are not. And that is a gap in our, going to be a gap that's it's going to be glaring in our record for many, many, many years. People will be thinking back to this year. But to the extent we can maintain that continuity, the satellite record will continue, and that's good. Finally, I mentioned Arctic residents provide a frame of reference that predates that satellite record, and that's a resource that we can continue to tap to understand more about greening and browning and what it means for people. Finally, I don't have, this is by no means all just work I've done. It's all involved a whole lot of people in different parts of the world. And I just not going to name too many names, but just I'll end with a couple of photos that show, it takes teams to do this kind of work, a lot of different skills and personalities and capabilities. And it's been a lot of fun. It's what makes doing this work so much fun. So with that, I'll sign off with Quyana, which is a common word you'd hear on the YK Delta. Thank you, and be happy to answer any questions.
Thank you, JJ. That was a great presentation. We have a few minutes for questions and answers, and I want to note too that JJ said that he'd be available for an additional 10 to 15 minutes after the top of the hour if people want to plan to stay around and ask questions. A quick reminder, if you're on Zoom, ask your questions by typing them into the chat box, and I'll read them aloud. If you join in on YouTube, again, type your questions into that live chat box, and Kuba will share those with me. And if you're joining by phone, you'll need to press *9 to join, and then *6 to mute yourself. The first question we have is from Robert Bukowski, and he was asking, do we have data to determine whether greening versus browning is different at wet versus dry sites?
Yeah, good question. I talked a little bit about surface water, but I think your question is getting at hydrology, right? So, and yeah, that's a very good question. So, I'm going to think of a particular example I'm familiar with in northern Alaska on the coastal plain, where you have a lot of microtopography that's related to permafrost. So high spots, low spots, and you can go from places where you could set with your bare foot, and then the next step you'd need hip waders, right? And so I would say, for one thing, like the wet areas are actually can be the very difficult ones in order to really understand, because their greenness dynamics, the vegetation is influencing NDVI, but the amount of surface water is influencing that also. And there's a lot of interchange, if you will, where changes in that hydrology can affect the plants. So it does get pretty complicated. I think in general, when I look at these trends, my eye I tend to focus on, I would say, more in upland areas, where you have, I would say, there's fewer sources of variability, right? Um, and those are, for example, the places where we see a lot of shrub increase or changes in shrub abundance. And those get a little bit easier to interpret. The wetter areas are a bit of a problem. And, we have different ways to address that. You can use different satellite sensors, for example, the more high resolution sensors, where you can begin to parse a little bit what's going on in the wet areas versus drier areas. So I'm not sure I really did a great job addressing your question. I would say that there's a lot of uncertainty, particularly when you get in really wet coastal plain environments. A good term to use is water can confound. And confound is a word I hate. I don't like things that confound the issue. Surface water certainly can do that. And so we have to be cautious in how we interpret some of these trends where we know there's variability in water.
Thanks, JJ. I'm going to take another question, and then I'm going to share a quick slide asking people to give feedback before the top of the hour, and then we can continue the Q&A for another few minutes as you're available. Also, so everybody knows, I will copy the chat. I'll copy the questions and share them with JJ so that he can respond to folks later if that's available. I think Martin Pilote asked a very similar question. That was how greening or browning will impact. How will greening or browning impact thawing permafrost and aquatic systems?
Yeah, good one. So in thinking about permafrost, when I first came to Alaska, I think when just about anybody who's first getting introduced to the topic of permafrost, your mind maybe instantly goes to, well, it's permafrost, it's frozen ground. If it's a cold place, that's where permafrost develops, and it seems simple, but the ecosystem is really important in terms of the development and the fate of permafrost. So as you grow vegetation on top of frozen ground, that vegetation is serving to insulate and shade that surface. So essentially, it's protecting permafrost. If you have an area that's greening, say, for example, you're increasing shrub abundance or something like that, there's a lot of reasons that could happen. But if it's happening on a site with permafrost, oftentimes what can happen is that added vegetation is actually serving to buffer the permafrost beneath from the air above. So you can actually protect permafrost by growing more vegetation on it. That's actually one good way to protect permafrost is put more plants on it. So that's an example where greening actually could indicate stable conditions in permafrost. The browning, I'd say most commonly, it is very common to see browning associated with permafrost degradation, because as that surface collapses, as the ground ice goes out, oftentimes whatever vegetation was growing there was not adapted to growing in the water. It collapses and it drowns essentially. So frequently when you see browning at fine scales in the Landsat record, that'll pick out places that where you've lost permafrost. But it can be challenging because today's browning, like where you've created some change and the vegetation has died off, today's browning is tomorrow's greening. So project forward 10 years, that new site that's wet is colonized by plants that do well in wet environments, and then they grow and you could get a greening signal. So it can be pretty tough to look at these trends at a global scale and really state with certainty or really specifically what it means for, it's very site dependent, is the best, I guess, way to put it. But you can see different NDVI responses to these different processes, or even the same process, depending on the window of time you're looking at.
Rather than change screens, I'm just going to go ahead and invite people to use the link that Stacy shared for the survey if you're leaving, and that's at www.htus, and it's goo.glyz, 3QT. So there's a link that's in the chat. You can go to that. But I'll also say that the presentation is going to be archived, and we'll have a link to that feedback in the archive, and also in a message that will go to everybody that has registered for the webinar. Some folks will be leaving us now since it's 10 o'clock, but JJ has agreed to stay for next few minutes, and I'll continue to read the questions as they come in and welcome people to continue to ask them. JJ, you can probably see on the chat that many people are saying thank you for an amazing talk. And I wanted
Oh, cool. I actually didn't see that. There it is.
Yeah,
Well,
there's
thanks,
a lot
everybody.
of great feedback, and people are enjoying the talk. And we certainly on ARCIS appreciate everybody joining us today. So with that, I think I'll go back to the next question. And that a couple questions came from Vladimir Romanowski. And one, he was asking about your comment that Pinatubo eruption impacted the NDVI minimum, and wondering if you saw the same thing in 1992 eruptions or subsequent eruptions.
Let's see. So the Pinatubo was the biggie that is captured in that record from. I would try to go find that slide. It would probably take me a little while. There certainly were other eruptions that had a big impact in the Arctic and globally. I think Pinatubo was the most distinctive one. I know in the 80s, I'm blanking on the year, but Chichon was an event down in Mexico that had an impact. So certainly, if you took that time series and you found there's certainly distinctive features there, years that are way up or way down, and yeah, certainly a few of those do have to do with eruptions. But of course, every eruption is different, and how much ash is entrained up in the upper atmosphere, where it has a way of then getting to the Arctic and really directly impacting climate there. So I'm trying to think of more recent eruptions that were big enough to really have a noticeable impact at a circumpolar scale. And yeah, Pinatubo is really the big one. But if we had a record that extended back farther, for example, like if we went back to 1912 in the Katmai eruption in southwestern Alaska, or if I can really dream, if you went back to Krakatoa or any some of these, we know those things they must have had a really immense impact. But we certainly know some of them did, just based on the stories of just how people lived through some of these seasons where it disrupted agriculture in temperate latitudes. But yeah, certainly it's one of those things that's creating a lot of that variability that we see in the record.
Thank you. I'm thinking the next question, I believe, came from Naticha, and I'm probably mispronouncing your name, Nikita Deshpanda. She says, thank you for this wonderful and inspiring presentation. Out of curiosity, what impacts do greening and browning have on Arctic surface albedo and temperature? Thank you again.
Yeah, that's a good one. One of the last things I did before I said no more to the slides and got out of that is I deleted a slide that would have addressed this very question that had to do with albedo. So in general, greening, I think, is something that is going to tend to cause albedo to decline, at least in the winter. And it's pretty easy to imagine. If you imagine low-growing tundra, in the wintertime, you get complete snow cover, and it's essentially a uniformly white surface, highly reflective. But as soon as you start adding trees or tall shrubs or anything that has a canopy that's sticking out over the snow, that projecting vegetation is much more effective at absorbing radiation than it is at reflecting it. It's most obvious if you're flying over the landscape in the winter and you fly over, say, a spruce forest versus a deciduous forest, or any kind of forest, and then tundra. In general, greening, if you're talking, there's more plants, than the plants that are there are getting bigger. In general, that's going to cause albedo to decline. and particularly in that important period in the late winter when there's enough sun that it actually matters, and can also have an impact on local snowmelt. And there's a sort of a feedback mechanism there. As you lower albedo, you promote further warming locally. With brown, and just to add, I guess with browning, it can be, it depends. If you're browning and that is associated with an increase in surface water is very effective at absorbing solar radiation. So browning, if it means more surface water, that could certainly cause a decline in albedo also.
Thank you. We have a couple follow-up questions from Vladimir, and he said that his question was actually about the 2018 minimum. The question about Pinatubo.
Just to commenting on 2018 in particular?
Yeah.
So I may not be the best person to answer this because I'm not an atmospheric scientist, but my understanding of 2018, well, a lot of my understanding of 2018 is driven by the fact that I live in Fairbanks, and I was doing a lot of field work that year. 2018 didn't seem that chilly, in particular here in Alaska. I think the places that were most affected by that is more in the Canadian Arctic and in Greenland. I know just from people I've talked to that work in those areas, and certainly from some of the literature, there was a very late spring preceded by a lot of snow the preceding winter. So snowmelt was really late, green up was really late. There were a lot of it affected, there were a lot of reproductive failures in, for example, migratory birds and other animals in those areas. So it was a pretty stark reversal of the general trend that we've seen towards longer, warmer growing seasons. And how that, why exactly that occurred, it was most pronounced in that part of the Arctic. If you look at Eurasia, actually, it really wasn't very cold at all. It was more typical. So why that, kind of what the broader scale circulation patterns or why that got set up, I can't comment very well on that. But I guess the interesting thing is that the very next year, 2019, in many of those same locations in the Canadian High Arctic and Greenland, they had record warmth. So there's kind of a whiplash there. And that's why I'm really curious to see what we learn as we add more years to this satellite record, because Arctic vegetation it's not just what the weather is today that's affecting the greenness. Arctic plants, they're perennials. They live a very long time. And so the productivity in one year I think is largely sort of preordained, if you will, by the conditions the preceding year. Because if you had a cold summer, those plants, as fall comes, they haven't hardened off the winter buds, and there's all sorts of things that are going to influence how they do the next year. So that's one reason I said stay tuned in the conclusions.
Thanks. Tom Douglas asked, he says, awesome presentation. And he says, can you link greening or browning to ice content, thaw subsidence, and deeper thaw that could allow for more shallow subsurface water storage? I assume the areas of thaw that are wetter and can allow for more water storage and thus happier plants are greener. But what do you think?
Yeah, good one. So as I think I've said a few times, it depends. I guess thinking of, in broad terms, with permafrost distribution, generally speaking, I would say places with discontinuous permafrost where you've got, fragmented permafrost, where as permafrost continues to degrade and water has more ways of moving laterally through the landscape, and in some cases essentially becoming unavailable for plant growth. In some cases it can percolate downward deep into the ground in places it maybe couldn't do formerly. And so it can be very mixed. I mean, I think in a lot of those cases, if you're promoting better drainage, it could actually promote better plant growth. In some circumstances, though, it could be just the opposite. I mean, the Arctic is, it's a cold place. It's hard to evaporate a lot of water out of it, but you certainly can create places where the growing conditions become quite dry, and you can get a big dieback of vegetation as a result. I guess thinking in colder parts of the Arctic with continuous permafrost, you have a little deeper thaw, and the water, still doesn't really have as many places to go. So yeah, it's tricky. It's again is trying to generalize these patterns of greening and browning. It can be difficult to do. Because we know there's a lot of that greening and browning is happening against a backdrop of warming temperatures in general. But there's all kinds of local scale things that are influencing those trends at a particular site. So I think I didn't really get to your question very well, Tom, but yeah, we can talk again. I know where to find you.
Yeah. We have two more questions that I have come in, and then we'll close. The first one is from Sakshi Mankocha, and the question is, does permafrost behavior have a relationship with climate change, and specifically to the warming oceans?
Well, the answer is yes. So I'll maybe work backwards. I won't talk too much about oceanic processes, but if you're thinking of the Arctic and in a global sense, and by in this case I mean both on land and the marine environment too. Oceanic circulation is really a key part of global change right now and climate change, because there's so much heat storage in the ocean, and this turnover of surface water to bottom water, much of which happens in the Arctic during freeze up in the Arctic Ocean. That's one good way to exchange water, and that's kind of powering the global pump, if you will, that's moving ocean water around globally. Big part of that. So these things are really tied together, and I suppose the extent with permafrost, a major challenge and research question now has to do with just how potent all of the carbon that's stored in these organic soils that are frozen. When to use a metaphor that's certainly not original, when you take your freezer and turn it into a refrigerator, things happen over time, right? And so you're potentially mobilizing a lot of that carbon, which can then feed back to climate, and so all these things are kind of wrapped together. Bringing that to greening and browning, I mean, I guess just speaking of the carbon cycle in general, I just mentioned permafrost, obviously, and permafrost carbon. When we're looking at greening and browning, one thing I've been talking about it mainly in terms of the vegetation and what it might look like and what its structure is and so on. But wherever you're seeing an increase in vegetation, there is some implication for the carbon cycle there, and that the plants at that time, when they're becoming more productive, they're sequestering carbon in their own tissues. Now, that carbon may not stick around very long. It may not be put into long-term storage. So it may not be all that important in terms of the global carbon cycle, but we can't neglect it. So kind of a wide-ranging answer to your question there. Hopefully I kind of addressed some of what you were curious about.
Thanks. And one last question we have is from Kirk Scanlon, and he asks, what role, if any, can you see near surface geophysics playing in understanding the spatial and temporal variability in the tundra, specifically with respect to understanding?
Yeah, I like it. No, I think you remember earlier, I alluded to the challenges. Obviously, remote sensing of permafrost permafrost is a subsurface condition, right? And there's a lot of ways it manifests on the surface, and you can make inferences about whether it's there or not, certain aspects of permafrost. But yeah, in terms of remote sensing, these geophysical measurements, I mean, I've not worked with those data much myself, but I'm really really impressed by the what's possible, and it's really interesting technology. I guess there's certainly been a lot of efforts to develop technologies that are where you can make these sorts of observations over larger and larger scales. There's ways to do that indirectly through measures of soil moisture and so on. But a lot of these geophysical instruments that I am familiar with to some extent, they're things that tell you something about the place you are at, on the ground, very local. Or you can put it on maybe on an aircraft and fly an area. But yeah, I think that's in terms of the remote sensing toolkit and growing that toolkit and working, using the tools in a complementary way, like those geophysical methods seem to be, really a very promising area, which I think would be very important for understanding more about the causes and consequences of the NDVI dynamics.
Thanks. And we did have one more question come in that I'll go ahead and ask. It's from Sergio Vergas Zasati. And he says, I'm curious if you have used historical airborne imagery for parts of Alaska to explore change over time. Also, do you know if these data sets are freely available?
Yes, I have. And they are, a lot of it is freely available. So one really great resource is basically, if you just, I would say the first place to go is US Geological Survey Earth Explorer website. And you can access, for Alaska, really an enormous archive of historical vertical aerial photographs, many of them from around 1950. This was photography that was flown back when they were developing topographic maps for the state. And so the coverage is really impressive. And it's also, the timing is good. I mean, you're getting like right around mid 20th century. So that's a really nice time period to have high res imagery. And a lot of that is at your fingertips on that website. There's a little learning curve in how to use the site, but basically you just select, you go in there and you can select different data sets to search and then define your search area. The same applies for the spy satellite photography. It's shown on that site as declassified data, I think, is if you see the word declassified, that's what you want to look at. And obviously those systems were developed to keep an eye on the Soviets primarily, but these satellites carried an immense amount of film, and they were burning film in lots of really out of the way places, including different parts of Alaska. And just in the last few years, the latest, I suppose the last of the spy satellites that ran using analog systems, so physical film, it's called Hexagon, and it's very high resolution, and there is a lot of coverage for Alaska. I've just sort of started to peel back the top layers. So there's a lot of information, and I certainly use some of that to look at, for example, you can look at individual trees, you can look at changes in tree lines, changes in water bodies, all sorts of things. So at high resolution, and it's a powerful tool. It can be a little tough to use because it's black and white photography. So a lot of you can't calculate NDVI using that, but you can use your eyeballs. And there's certainly other ways you can analyze that data to look at change in a pretty engaging way, I think.
Thank you, JJ. I think at this point we'll close. I want to thank you especially for not only a great presentation, but for willing to stick around for another 20 minutes to answer questions and to—
I'm on my back porch, so.
So it's comfortable.
No problem.
And we had 35 people that continued to stick around. I really appreciate everybody's participation today. I'm going to go ahead and share the final slide that shares information.
There you go.
Saying that we've got, we'll be archiving today's seminar, and for information about future seminars, please, you can visit ARCIS at www.arcis.org. And this seminar has been recorded and will be archived on arcis.org research seminar series /archive. And again, we certainly welcome everybody's feedback. Stacy shared this link in the chat, which you can link onto there, but it's a short seminar evaluation, and we'd really appreciate some feedback and help us to develop future events and webinars. So at this point, we'll close the webinar and wish everybody a good and healthy day. And again, thank you very much to JJ for your great presentation, and thank you to all the participants for some excellent questions today. I think we had good discussion. Have a good day.